Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
In the intellectual landscape of the late 19th century, a period of profound re-evaluation across science and philosophy, few questions struck closer to the heart of human certainty than the nature of space itself. For over 2 millennia, the edifice of Euclidean geometry stood as the paramount example of irrefutable, necessary truth, its axioms and theorems seemingly woven into the very fabric of reason. This towering certainty found its most powerful philosophical defender in Immanuel Kant, who enshrined Euclidean geometry within his critical philosophy as a form of synthetic a priori knowledge, a structure imposed by the mind upon all possible experience of the outer world. It was into this charged environment that the polymathic genius of Hermann von Helmholtz intervened. His 1882 lecture on the origin and significance of geometrical axioms stands as a landmark of scientific empiricism, a quiet revolution in thought that dismantled the Kantian conception of space and refounded geometry upon the bedrock of physical experience. This essay was a masterful synthesis, translating the arcane discoveries of non-Euclidean mathematics into a lucid and compelling philosophical argument, thereby clearing the conceptual ground for the geometric revolutions of 20th century physics. The genesis of Helmholtz's inquiry lies in the confluence of two powerful intellectual currents: the philosophical system of Kant and the mathematical heresies of the non-Euclidean geometers. Kant, in his critique of pure reason, had argued that space was the pure form of our outer intuition. The axioms of Euclid, such as the famous parallel postulate, were necessary truths because our minds are structured to perceive and organize sensory data within a Euclidean framework. One could simply imagine a different logical system. One could never, according to Kant, genuinely intuit or experience a world structured by it. This view provided a formidable philosophical bulwark for the uniqueness and necessity of Euclidean geometry. However, beginning in the early 19th century, mathematicians had begun to chip away at its logical foundations. The independent, almost secretive, work of Carl Friedrich Gauss, followed by the publications of Janos Bolyai and Nikolai Lobachevsky, demonstrated with unimpeachable rigor that one could construct perfectly consistent geometries by negating Euclid's parallel postulate. In these new, strange worlds, the sum of angles in a triangle could be less than 180 degrees or greater than 180 degrees, and parallel lines might either diverge or inevitably intersect. This created an acute philosophical problem. If multiple, contradictory geometries were all logically sound, then on what basis could one claim that Euclidean geometry was the one true geometry of physical space? Logical necessity had failed as a criterion. The decisive mathematical breakthrough that provided the language for a new understanding came from Bernhard Riemann in his monumental 1854 habilitation lecture on the hypotheses which lie at the foundations of geometry. Riemann generalized the very concept of space. He introduced the idea of an n-dimensional manifold, a space whose geometric properties are defined locally by a metric that determines the distance between infinitesimally close points. The character of this space, its geometry, is determined by a quantity Riemann called curvature. Euclidean space is merely the simplest case of flat manifold with zero curvature. Spherical surfaces possess constant positive curvature, while the geometries of Bolyai and Lobachevsky correspond to spaces of constant negative curvature. Riemann's vision was breathtaking in its abstraction and generality, suggesting that the geometry of our own physical space was an empirical question, something to be measured and discovered, whose global structure was entirely unknown. Riemann's work, however, was immensely dense and mathematically demanding. It required a translator, a bridge builder who could connect its abstract formalism to the world of tangible experience and perception. This was precisely the role that Hermann von Helmholtz, with his unparalleled expertise in physics, physiology, the psychology of perception, was uniquely qualified. Helmholtz 1882 essay executes this translation with brilliant clarity. He confronts the Kantian position directly, proposing a radical alternative. The axioms of geometry derive their certainty and their content from experience. They are inductive generalizations, summaries of our repeated, uniform observations of the physical world. The core of his argument rests on a profound insight into the relationship between measurement and the behavior of physical objects. The entire practice of geometry, he contends, is predicated upon the existence and free mobility of rigid bodies. Our very concept of congruence, of one shape being identical to another, depends on our ability to move an object from one location to another, to rotate it and compare it with other objects, all while assuming that the object itself remains unchanged. A measuring rod, when moved, must measure the same length. This seemingly trivial observation for Helmholtz, is the empirical key to the entire structure of geometry. The Euclidean axioms describe a space in which this readability of rigid bodies is possible in an unrestricted. To make this point viscerally clear, Helmholtz employs a series of ingenious thought experiments, inviting his audience to imagine the worldview of intelligent beings inhabiting spaces with different geometric properties. He first imagines two-dimensional beings living on the surface, a giant sphere. For these creatures, the shortest path between 2 points, their equivalent of a straight line, would be a great circle. If they were to construct a triangle from these great circle lines, they would find through measurement that the sum of its angles is always greater than 2 right angles. Their experience of moving their rigid measuring rods around on this curved surface would lead them to codify the axioms of spherical geometry. They would find Euclid's parallel postulate absurd, a proposition contradicted by every observation they could make. Conversely, he asks us to imagine beings on a pseudospherical surface, a shape of constant negative curvature. Their empirical measurements would lead them to a Lobachevskian geometry, where the sum of a triangle's angles is always less than 180 degrees. Perhaps his most subtle and powerful thought experiment involves a convex mirror. He imagines intelligent beings living on the surface of a sphere, but whose bodies and measuring instruments shrink as they move away from the sphere's center toward its equator, a process governed by a specific physical law. To an outside observer, their world is finite and curved. To the inhabitants themselves, whose experience is entirely determined by their shrinking measuring rods, their world would appear infinite. When they attempt to construct straight lines, the paths they trace would conform to Euclidean axioms. Their empirical reality would compel them to believe they inhabit a flat, Euclidean plane. This example is a masterstroke. It demonstrates that the geometry we perceive is a combined product of the underlying structure of space and the physical laws governing our measuring instruments. We are unable to disentangle the two. The supposed a priori certainty of Euclidean geometry, Helmholtz concludes, is a contingent artifact of our experience in a world where, at the scales of everyday life, space is very nearly flat and our measuring devices behave like ideal rigid bodies. The axioms are empirical facts. The truthfulness is a matter for physical science to investigate. The impact of Helmholtz's argument was immediate and profound. It provided a coherent and accessible philosophical framework that legitimized the new geometries and situated them within the domain of empirical science. His work posed a formidable challenge to the dominance of neo-Kantian philosophy in German academic circles, shifting the terms of the debate from pure reason to physical investigation. The subsequent development of this line of thought, however, reveals a subtle but significant refinement. The French mathematician and physicist Henri Poincaré, while deeply influenced by Helmholtz, proposed a philosophy of conventionalism. Poincaré agreed that the axioms of geometry were definitions, the truth established by choice. He diverged from Helmholtz's pure empiricism by arguing that the choice of which geometry to use for describing the world was a matter of convention, guided by convenience. One could, Poincaré argued, always preserve Euclidean geometry by postulating complex and strange physical laws to account for any observed deviations. For example, one could explain the bending of light near a massive object by saying that space is flat but that light rays are acted upon by a force. Alternatively, one could say that space itself is curved and that light follows the straightest possible path, a geodesic, within that curved space. Poincaré believed that scientists would always choose the former option, retaining the simplicity of Euclidean geometry at the cost of more complex physics. It was a choice of descriptive language, a convention. It is one of history's more delightful ironies that Albert Einstein would ultimately prove Poincaré wrong by proving Helmholtz right in the most spectacular fashion imaginable. The development of the general theory of relativity represents the ultimate vindication of the Helmholtzian perspective. Einstein, who explicitly acknowledged his debt to both Helmholtz and Poincaré, took the radical step that Poincaré deemed inconvenient. In general relativity, the geometry of spacetime ceases to be a fixed, passive background. It becomes a dynamic physical entity, a four-dimensional manifold whose curvature is determined by the distribution of mass and energy within it. The gravitational field is the curvature of spacetime. The axioms of geometry are determined by the contents of the universe itself. This was no longer a matter of convention or philosophical debate. It was a physical theory with testable predictions. The confirmation of such prediction, the bending of starlight passing near the sun observed by Arthur Eddington's expedition during the 1919 solar eclipse, was a world historical event. It was the first empirical proof that the geometry of our universe is non-Euclidean. The physical world had spoken, and it had declared that the axioms of geometry were indeed empirical facts discovered through observation and experiment. The philosophical groundwork laid by Helmholtz had become the operational reality of fundamental physics. In conclusion, Hermann von Helmholtz in his 1882 essay on the origin and significance of geometrical axioms, occupies a pivotal position in the history of modern thought. It served as the crucial intellectual bridge connecting the abstract mathematical innovations of Riemann with the concrete physical revolution of Einstein. Helmholtz possessed the unique polymathic synthesis of knowledge in physics, physiology, and philosophy required to see the empirical heart of the geometrical problem. He methodically dismantled the Kantian claim of a priori certainty, demonstrating with lucid thought experiments that our geometrical intuitions are forged in the crucible of physical experience with movable, rigid bodies. His work transformed geometry from a branch of pure mathematics, a system of immutable truths, into an empirical science, a chapter in the larger book of physics, while Poincaré's conventionalism offered an elegant and enduring philosophical alternative. It was the core Helmholtzian insight that the structure of space is a physical question to be settled by experiment that animated the new physics of the 20th century. His essay remains a timeless testament to the power of empiricism and a profound reminder that even our most deeply ingrained certainties about the nature of reality are hypotheses, subject to revision in the face of evidence. Helmholtz taught the scientific world a lesson of monumental importance. The axioms we hold to be self-evident are often merely the ingrained habits of a mind shaped by a limited slice of a vast and surprising cosmos.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.